Hey guys, this video is about units of solution concentration. So we'll start with molarity. You should be familiar with this already. Molarity is defined as moles of solute over liters of solution. So in this equation here, molarity is N over V. We can solve for any of these variables given the other two. Given the molarity and the volume, find the moles, for example. So let's do an example. Here we're asked to find the molarity of potassium bromide in a solution that's made by dissolving 519 milligrams of potassium bromide, and I give you the molar mass there, in enough water to prepare 150 mils of solution. So why don't you guys work this out real quick and come on back when you get an answer. Welcome back. So we need moles of the solute, which in this case is potassium bromide. So to get that, we take the mass and divide by the molar mass. Now, we were given the mass in milligrams, and all I did is something we do a lot, is I moved the decimal 3 to the left to convert milligrams to grams. But we have to make sure we do that. And so now we have the N, the moles of the solute, potassium bromide. The liters of solution, we were told it is 150.0 milliliters, and I did the same thing as I did with the milligrams. Because this was milliliters, and we have to have liters in the denominator, I moved the decimal 3 to the left. To give us the 0.1500 liters of solution. Divide these two numbers, we get 3 sig figs. There's our answer. We would say that the concentration of potassium bromide in this solution is 0.0291 molar, or the molarity is 0.0291 molar. Mass percent is defined as the mass of the solute over the mass of the solution times 100. Another way of writing this is taking the mass, or the grams of the solute, divided by, well, it has to be grams actually, grams of the solute per 100 grams of solution. These are equivalent, but they're you'll use one form or the other depending upon what's easier for you. So let's do an example. We want to find the mass percent of sodium iodide in a solution whose density is 1.59 grams per milliliter and whose molarity is 0.519 molar. So why don't you guys work this out and come back and get an answer when you get an answer. A hint is assume exactly 1 liter of solution. All right, welcome back. So assuming 1 liter of solution, that means if it's 0.519 moles per liter, we know that we have 0.519 moles of sodium iodide. So we can get remember we need grams of the solute, or mass of the solute over the mass of solution times 100. So to get the grams of the sodium iodide, we just multiply by its molar mass, and that gives us 77.8 or so grams. That's the numerator. Now, because we were told that the density of the solution was 1.59 grams per milliliter, and we assumed exactly 1 liter, or 1,000 milliliters, that means we have, of solution, we have 1,590 grams of solution, 1.59 times 1,000. And so we have the denominator. So grams, the mass of the solute over the mass of the solution times 100 gives us 4.89 mass percent sodium iodide in this solution. Next, mole fraction. The mole fraction of component A, whatever it is, or chi sub A. Chi stands for mole fraction here. It's just defined as the moles of that component divided by the total moles in the solution. So let's do another example. We make a solution by adding 0.237 moles of ethyl ether to 0.519 moles of ethyl alcohol. What's the mole fraction of ethyl ether? Go ahead and work it out real quick. Come on back when you get an answer. Welcome back, guys. So this one's real easy. The moles of the ethyl ether, EE stands for ethyl ether here. The mole fraction is the moles of the ethyl ether over the total moles. So we were told how many moles of ethyl ether we have. Total moles is just the sum of the moles of everything in solution. So 0.237 plus 0.0519. And so we get a mole fraction of ethyl ether of 0.313. That's all there is to that one. The next one, molality. Now, this is very similar to molarity, and the symbols, the word is very similar, only one letter difference, molality with an L instead of molarity with an R. And the symbol is a lowercase m rather than a capital M like it is for molarity. And also, both of them have moles of solute in the top. The difference is we have kilograms of solvent in the bottom for molality, liters of solution in the bottom for molarity. Now, for low density solutions, this and dilute solutions, this one's the two numbers usually are pretty close. But when we get away from that, they're not necessarily. The reason we have molality is because it does not depend upon temperature. If you think about it, molarity, moles of solute over liters of solution, well, the volume of a solution depends upon the temperature. Most of the time, if you heat it up, it's going to expand. Cool it down, it's going to contract. So the denominator in the molarity equation changes with temperature. But molality, this does not. The mass of the solvent doesn't change. Doesn't matter if we heat it up or cool it down. The mass does not change. Neither does the moles of solute. So this is why we have this right here. So let's do a little example with molality. So we have a solution that contains 398 grams of potassium chlorate per liter, and it has a density of 1.222 grams per milliliter. What's the molality of the resulting solution? So guys, go ahead and work this out real quick. Come back when you get an answer. Once more, we're going to want to assume we have exactly 1 liter of solution. Welcome back. So if we have exactly 1 liter of solution and the density is 1.222 grams per milliliter, we have exactly 1,000 milliliters. We have 1,222 grams of solution. Now, because we want in the denominator of the molality equation the kilograms of the solvent, which is water here, to get the mass of the solvent of water, we take the mass of the solution minus the mass of the solute, which in this case was potassium chlorate. So when we subtract these two numbers, this gives us the mass of water in grams. Kilograms, just move the decimal 3 to the left. Now, to get the moles of the solute, well, we know the mass of the solute, which is potassium chlorate, divide by the molar mass, that gives us the moles. Divide these two numbers, and we would say that this solution is 3.94 molal in potassium chlorate, or the molality of potassium chlorate in this solution is 3.94 molal. And normality. Normality is defined as equivalence per liter of solution. Now, what an equivalent is depends upon what is in the solution. So if we're talking about an acid, then 1 equivalent is equal to 1 mole of protons that can be donated. In other words, for every 1 acidic proton there is in an acid, there's 1 equivalent. So for example, if we have a solution that is 1.5 molar in phosphoric acid with 3 acidic protons here, then the normality of that phosphoric acid in that solution will be 3 times that, or 4.5 normal, because we have 3 acidic protons. So that means we have the number of equivalents is 3 times the number of moles. If we have 1 mole of phosphoric acid, we have 3 equivalents in that solution, because each of these protons is an equivalent. So all we do is we take the molarity times the number of acidic protons, and that gives us the normality. Now, if it's a base we're talking about, 1 equivalent is equal to 1 mole of protons that can be accepted. And usually this is, not all the time, but most bases we see at this point are metal hydroxides, but not all of them. In this case here, if we have a 2.2 molar solution of calcium hydroxide, because there are 2 hydroxides in 1 calcium hydroxide, we have 2 equivalents for every 1 mole of calcium hydroxide. So that means if we have twice the number of equivalents as moles, if we have 2.2 moles per liter, we have 4.4 equivalents per liter, or we would say the normality of this solution is 4.4 normal. And then finally, for a redox reaction, where we have electrons being donated and accepted, 1 equivalent is equal to 1 mole of electrons that can be transferred for a redox reaction. So for example, if we have a solution of iron 3, because this has a positive 3 charge, the iron 3 ion can accept 3 electrons to make it an iron metal. And so that means that if we have a 0.125 molar solution of iron 3, it is 3 times 0.125 or 0.375 normal iron 3. So let's do another example. We're going to calculate the normality of the ruthenium-4 ion in a solution that's prepared by dissolving 2.055 grams of ruthenium-4 sulfate in enough water to make 375 milliliters of solution. So why don't you guys work this out and come on back when you get an answer. Welcome back, guys. So, first thing we're going to do is find how many moles of ruthenium-4 we have. Once we know that, we can find the number of equivalents. Because ruthenium-4 has a positive 4 charge, it can accept 4 electrons, and we'll have 4 times the number of equivalents as we do moles. So to find the moles of ruthenium-4 sulfate, we need the molar mass. So there's ruthenium-4 sulfate, divide by the molar mass, and we find moles of ruthenium-4 sulfate. And because in this formula we can see that there's 1 mole of ruthenium-4 for every 1 mole of ruthenium-4 sulfate, and we just talked about how there are 4 equivalents for every 1 mole of ruthenium-4, this works out to be 0.02804 equivalents in this solution. And to get the normality, we just take the number of equivalents, divide by the liters of solution. 375 mils is 0.375 liters, and we would say that this solution is 0.0748 normal. And that's all there is to it, guys.